This is yours. Is that yours? Oh, good. Yeah, no, it's all right. I just have to read the work. All right, thanks all for coming. A full house today, which is nice. I'd like to welcome you on the lands of the Ngunnawal and Ngambri people who have been custodians of this beautiful piece of the world for tens of thousands of years. And I pay my respect to their elders, past, present, and emerging. I welcome you to today's RSES seminars. As it is a very short but a new tradition, I'm going to read out a couple of random news items that you would otherwise not hear. Only those people coming to the seminars are completely on top of the news. Nobody else will ever hear about it. One is that Penny King is a collaborator on a recently funded NASA proposal. And will be developing on instruments for use on landers going to Mars and Moon. So I'm sure if you meet her and talk to her about it, she'd be happy to talk about the details on this. And the other piece of news I have is that Lu Wei Yang, is she here by any means? You are here. You just sit down. I will embarrass you anyway. So Lu Wei is a postdoc in climate and fluid physics, and she was awarded the best ECR presentation prize at the recent Australian Ocean Modeling and Observation Workshop. I think that was last week, wasn't it? Or the week before. So congratulations. Good to have you here. And you spoke at that workshop about a novel tide parameterization for Australia's next generation ocean model. And I'm sure at some point we will hear about this maybe at a seminar. So, and on this, I will hand over to the person introducing Megan today. Not Megan. Morgan, yeah. Something with M. And I'll hand over to Mark.
Awesome, okay. Well, yeah, thanks a lot, everyone. I'd like to introduce Morgan Blades, who's given our seminar today. Morgan is visiting us from University of Adelaide. She's actually an Adelaide lifer, so she did her undergrad and PhD there. And she started out life as an igneous geochemist, did a PhD on the kind of assembly of East Africa and so on, before seeing the light and transitioning into sedimentary basins, which are much more interesting, Mav. Yeah, and so today, so Morgan heads, she's a part of a huge group who are studying the kind of basins, Proterozoic basins across Australia, but particularly focusing on the McArthur Basin in northern territories and so on. So that's what we're going to hear about today. And one of the things that really impresses me about Morgan, and kind of I view her as a bit of a role model on, is the number of students that she is a mentor for. They have a huge group there, and she takes a lot of care over encouraging our kind of next generation of researchers into earth sciences. And it's something that I think it's just very impressive. So thanks for all your work, and I really look forward to hearing about McArthur.
All right, thank you so much, Mark. They're very kind words. So as Mark said, I'm Morgan. I'm all the way over here from Adelaide, and I'm a part of the Tectonics and Earth Systems Research Group. And I know there's a lot of people really excited about a basins talk today. I've heard the murmurs in the room. But I'm going to be talking to you about 500 million years of basin sediments preserved in Northern Australia. So first of all, I'd like to introduce the team working. This is a part of a major linkage project. When it will change. Give it a few minutes. The suspense is building. There we go. So this is a part of a larger linkage project. This is headed up by Alan Collins, as well as Euro Farkash, Carl Spandler, Rosalind King, and Simon Holford. Now, these are all main theme leaders within our group. We also have the amazing Darwin Subaka, a postdoc, as well as Dana, Ananya, Johan, and Yasser. And these are all really fabulous PhDs, which are directly working on this linkage project. Not to mention our amazing partners, which over the years have shown us a lot of support. So Proterozoic Australia. So this is a map which was taken from Tegan Blakey's paper in 2017. It's a lovely gravity image. And we can see that it outlines the Western Australian Craton, the South Australian Craton, and more importantly for the talk today, the North Australian Craton. Now this extends from Western Australia through to Queensland in the east, and it takes up a large part of our Australian continent. And so the Mesoproterozoic is often described as the boring billion. However, if you think about the amount of time it records, it's larger than the whole Phanerozoic. And within Australia, we have Mesoproterozoic rocks, which form as a part of these basin systems, and these overlie our Archean and Paleoproterozoic basement, which forms up Australia. So I'm really going to be focusing in on Northern Territory, and you will see this map a lot here. These are just outlining the different terrains that we'll be looking at. So the McArthur Basin will be a thing that I say quite a lot today. South Nicolson Basin, as well as the Tomkinson and Birrindudu Basin, which is this orange over here. So the McArthur Basin was originally defined as a form of a sedimentary basin, which went from about 1815 through to 1320. This is the original map, which was done by Rawlings in 1999, and it really just made up this northeast part of Northern Territory, and it's all that sort of tan brown colour. Traditionally, it was divided into the northern and the southern McArthur Basin, and it was separated by this Europunga fault zone. And so what they did from there was they decided to create this horrific stratigraphy. This is just for the McArthur Basin for the north and the south. So Rawlings in 1999 decided we needed to simplify this. He could see continuity within the basin. And so he came up with these 5 main packages: the Wilton, the Favenk, the Glide, the Goiter, and the Red Bank. And as we continued on, so Rawlings really just looked at this sort of system through here in green. As we continue on, people began to realize the McArthur Basin was actually part of a much larger system. It also had similar rocks in the South Nicolson Basin, the Tomkinson Province. They had the Beetaloo subbasins, as well as the Birrindudu Basin. And this became what's known as the Greater McArthur Basin. It's an informal term, but it's flooded throughout literature. So to make this even bigger again, they looked further east and they decided that they could also correlate this to sediments in Mount Isa. So there's the same Mesoproterozoic sediments, and it's experiencing the same sort of environments as those in the McArthur Basin. If we go even further east from Mount Isa here, we also get Mesoproterozoic rocks that got caught up in the collision between Laurentia and the Australian continents at about 1.6. And so the extent of the McArthur Basin and the Greater McArthur Basin is just growing and growing. So if that wasn't enough, we've even now, well, not we specifically, but May in 2011 showed that North China, the North China Craton, has similar aged rocks. These are in the Yanliao Alocogen, and they correlated the sediments of the Roper Group in McArthur Basin to this Shimaling Formation. It has similar biostratigraphy, it has similar chemostratigraphy, and lithologically it looks quite similar. Another thing they found was that it also has this 1.32 large igneous province intruding the top parts of the succession, which is what we also have in the Northern Territory. So Uwe Kirschner in about 2020 sort of just came up with this idea that there was this epicontinental sea that existed within Nuna, and this encompassed the North Australian Craton, the North China Craton here, but it also extended into the South Australian Craton, the rocks of the Rocky Cape Group in Tasmania. Also, there are similar age rocks in the Belt Basin in Laurentia, in North America, as well as there are meant to be similar age rocks in Siberia, but it's a little hard to test that theory. And then this led to further work by Shangxi Cao, who has just published a 1.8 to present whole plate reconstruction. So I've labelled the colours so everyone can see. That's the North Australian craton here. So what we can see at about 1800 is we have this really extended continent where we have North China, Siberia, and the amalgams of Australia. At about 1640, we see Laurentia coming in to subduct and will eventually collide with Australia. By about 1450, Laurentia's rifting away. And then by about 1320, it's basically sitting on its own plate, quite separate from Australia. And this circle here represents roughly where the McArthur Basin is located in these reconstructions. And so what this really shows, so a lot of this is fantasy, obviously. We don't really know how things look, but it's a great starting point so we can test what things look like, 1.8 billion years ago. But what this really shows is people really thought McArthur Basin was just an intercontinental basin. However, we can see it throughout its history that it's been sitting in quite prominent positions. And it preserves a much longer history. So not only is it incredible for its fact that it's sort of sat through multiple supercontinental cycles, but also it hosts some of our major resources. So McArthur River Mine is the 7th largest zinc mine in the world. It also has 118 trillion cubic feet of gas. So they're thinking about going into production next year. But what's quite funny is this is some of the oldest petroleum in the world. And so actually, Alan sent me a magazine last week from the US where one of the geologists commented on the Beetaloo petroleum, basically saying this is the only 1.4 billion old sedimentary rock that has been preserved in the world. There aren't a lot of sedimentary basins around before the Precambrian. The Cambrian, there's just not a lot of sediment, you just have granitic rock. So I definitely think they might have a lot to learn when they come and look for petroleum in the Northern Territory. And this is some work done by Mark in 2020, which shows the lithosphere-asthenosphere boundary where he plotted base metal deposits, and you can see that they form right along that boundary. And if we plot the McArthur Basin on top, we can see that it's sitting nicely where we're getting these base metal deposits. So not only is it interesting tectonically, but it's also quite valuable for our industry partners, hence why we're working on a linkage. Okay, so the 3 main themes of this talk are going to be chronostratigraphy, chemostratigraphy, and lithostratigraphy. So I've taken this straight from our linkage proposal. The chronostratigraphy, the aim is to refine, develop, apply novel dating techniques and date packages temporally. I said that the wrong way, but you get what I mean. Chemostratigraphy uses proxies and chemical data to understand and constrain changes in redox, biological activity, and salinity. And lithostratigraphy builds maps and sections of packages to develop a sequence stratigraphic template. So these are really the main aims of this linkage. So back to the McArthur Basin, just to remind you, so the map on the left is just the distribution or surface distribution of the packages. So Wilton package is our youngest package in green, the Fervent in this purple, the Glide is in these pinks, the Goiter up here is in this salmon color, and the blue marks the Red Bank package. And just looking at this, we can see that the distribution of the Wilton package, the Fervent package, and the Red Bank package is much wider than that of these pink units of the Glide and the Goiter. And this outline here is just the Beetaloo subbasin, which is subsurface. So I'm going to take you through the Red Bank package. I'm going to take you through each of the units, show you some pretty geology photos. I think they're pretty. And so the Red Bank package is the basal unit. It sits unconformably over volcanics. These are around 1835 to 1810 million years old. And this system stretches till about 1700. So it's made up of a range of siliciclastic, conglomeratic fluvial rocks, which are also interspersed with volcanics and some shallow intrusives. And we've got some examples of, this is the Plumtree Volcanics. You can see the beautiful feldspars. That is part of the Paleoprote underneath the McArthur Basin. This here is Nitmaluk Gorge. And you see all those beautiful cliffs are actually the basal units of the McArthur Basin, the Mamadouia sandstone. And we can see these beautiful crossbeds and lag beds in the Mamadouia. And if you look in the background, you can also see some Aboriginal art from the Drown people, which dates back to about 40,000 years ago. And then we have them from other parts of the basin, the Tomkinson Province, as well as the Birrindudu Basin. The top of the unit, or the top of the red bank, has much more higher component of muds within the Willagarang Formation and silts. The goiter package now, this one is an elusive character. It's only outcrops in the northeast part of the basin. And it's called the Parsons Range Group. It goes from about 1710-ish to about 1660. These ages are very poorly constrained. The only photo I could find of it was from the 80s. So when I tried to blow it up, it wasn't any point really. But it only outcrops here in what's called the Walker Fault Zone. And I highly doubt that many geologists have gone to really look at it. The glide package, this is where our base metals are mainly found in. So we can see this in the Birrindudu Basin, the McArthur Basin, and the South Nicolson Basin. However, we don't really see this too much in the Tomkinson Province, and that's mainly due to we don't really understand stratigraphy that well. However, this goes from about 660 to about 1600 million years ago. And we have the beautiful rippled beds, crossbeds. Crossbeds are my favorite sedimentary structure, so they'll appear in most of these. We have the Coxco Dolostone, as well as these beautiful ore textures from the Tina deposit, which is in the Barney Creek Formation. The Favenk package, now this is made up of a range of carbonates, and at the base it is made of some siliciclastics. This is about 1580, and here we have beautiful examples of these stromatolites. We have cineresis cracks, so changes in salinity. We have halite pseudomorphs showing us an evaporitic environment. Another photo of crossbeds, because who doesn't like crossbeds? And some more beautiful stromatolites. And we see the Favenk package quite widely across the basin. Last but not least, the Wilton package. So this has the source rock for all the petroleum that's viable or commercial. And the Wilton package at the base is much more clastic. And as you go towards the top, you get higher organics, more muds, more silts. So these are examples of our source rocks in the Valkyrie Formation and also the Kayala Formation. We also have these members here which form lower down, and these form our much more clastic environment. So it's interpreted to be somewhat sort of shallow marine to fluvial into deeper water environments. Now, I'm going to take you on a whirlwind tour of detrital zircons. And this is so that we can get an idea of the provenance. So I'm not looking to try and date the absolute maximum depositional of these rocks. I'm more looking to see, can we correlate these across the basin, looking at their spectra. Now, I was going to go into explaining multi-scaling dimensional plots in a maths way, but I went to a geodynamics meeting today and they know a lot more maths than I do. So I'm not even going to try. However, originally people used channel density estimates and probability plots to show our zircon spectras. These are just peaks where there's the most data. And we used to just draw a line to correlate them up. However, our data sets are getting much bigger, and so the need for other ways of visualizing things became a bit of an issue. So we've started using multi-dimensional scaling plots. Now, this is by no means new to geology, but it's definitely new to detrital geochronologists, or newer at least. And so easiest way, and the only thing I need you to care about, is when two plot points here plot really far apart from each other, their spectrals are quite different, or there is a degree of dissimilarity between them. When they're closer together, like these 2 points, they are more similar. And that's all I need you to take from those. We're going to do the same whirlwind tour of the packages. So on the right, I've drawn up a generalized stratigraphic log of the lower parts of the package. We have the absolute ages in red on the right. Now, these little circles, the pie charts, they're broken up into age bins. So the greens are older, the purples are younger. And then I've just got the extent of the package there. So each one of the next slides will be the same sort of breakdown. The Aileron Province, these areas in red, Tanami, Pine Creek origin, Halls Creek origin. They're our terrains up here. That's the Pine Creek and Halls Creek. That's the Aileron, and that's the Tanami region. So we're really looking at surrounding regions. Now, if you could pick a pattern out of that, I will give you a prize, because it really just looks like randomly scattered dots. But we can see that it sits between the Pine Creek and the Aileron. So really, that's all I can say about this. Now, as we go up into the glide package, we can see in the sedimentology, we have much more clastic at the basal units, and these are going up into much more carbonate-rich units at the top. This here, the Barney Creek Formation, is where we get all the mineralization, dated about 1640. And again, you can see now I've put on the middle red bank package, so that's the data from the previous screen. And again, if you can pick out anything, that would be great. But all I can see is that we have the same spread going between Aileron, Pine Creek origin, and they're plotting very similarly to what we see in the units below them. And the Favenk package, again, similar sedimentology. We have plastics more towards the bottom, and we're getting more carbonate rich as we go up the succession. In the Birrindudu Basin over here, we actually have much more clastic material. And work that Ananya Deepak is doing in her PhD allows us to pick out some subtleties in the data. So she shows that the older packages, so the Wickham, which is down here, it trends in a younging direction up like this, up where we have the Seal Formation here. And we can see that this trend is showing us a variation in sources. So essentially, we're just receiving more detritus. Now, I've been talking about how these just look all the same. There's not really a pattern. I can't see variation. So, you know, for those people that hate detrital zircons, this is really proving their point. It's not really that helpful. Are we just looking at recycling of the basin? So are we just seeing, we've had lots of periods of basin inversion within McArthur Basin's history. So are we just looking at those sediments going through that system multiple times? So we get to the Wilton package. The Wilton package is much more exciting. Already I can see that there are two main dominant sort of clusters. Within the Wilton package here, this bottom part is much more clastic, silt rich. The difference between the Wilton package and most of the rest of the basin is it's only got very minor carbonates in it. And as you're going up in the succession, it becomes much more mud dominated. And at the very top, this is the Derrim intrusion, which constrains the youngest age of the basin at about 1313 to 1320. And what we can see from this plot is that the stuff in the Birrindudu Basin, which is here, and the Tomkinson Province plot quite differently to the stuff in the McArthur Basin. We can actually see something that Bo Yang presented or did in his PhD about 4 or 5 years ago, was that you can actually see a trend within the packages. So we can see that our oldest parts of the Roper group are very much located down here towards Aileron, and we see this progressive shift towards more eastern sources as we get to the Valkyrie Formation, which is this formation up here. And then it shifts back towards more southerly sources. So this is likely because, so we're getting a lot of derivation from 1580 Mount Isa. And this has been interpreted by Bow as to represent as Laurentia was rifting away from Australia. We had the uplift of the rift shoulder, and we had those sediments being sourced from the east. And so that's really neat. Now, this is the last MDS plot I'm showing you, I promise. I plotted them all on as packages, so we can see the glide package, the bottom parts of the Tomkinson Province, the Red Bank package, and the Wilton package in the Tomkinson Province and Birrindudu Basin. They all plot to the left. The stuff from the South Nicolson Basin and as well as the McArthur Basin proper all plot to the right. So this is really showing us this same sort of trend that we've seen in our Wilton package, that we don't really see this provenance divide until we get to the youngest sediments in the basin. So in this plot, just from our data, there are 11,282 separate data points of all concordant within 10% zircons. And so the more information you feed into these, the more powerful they'll be. So, but vice versa. So sometimes if there's not enough data, these are quite a hindrance. So now I'm going to talk to you a little bit about hafnium. So I've been talking to you about how we are sourcing places like Pine Creek origin, the Aileron province down here. Zircons like to take in hafnium, and hafnium is something where it allows us to understand the nature of the melt that zircon grew from originally. So this here is the depleted mantle line. Anything that plots close to that comes from the mantle with little interaction with continental crust. Anything down here, for instance, is basically we're reworking our continental crust. And so we can use this as a fingerprint to help us with provenance, to help us sort of understand. Because the thing about Northern Australia is the ages are all very similar. We have there are main peaks at 1750, 1850, 2.2, 2.5. And it's very hard to discern exactly where these come from. But what's interesting is we have these incredibly radiogenic signatures. These are at about 2.5. And look, there is a few other people like Tony Kemp and his colleague that he works with have also found this as well. And that this suggests when we have such a large array where we have both negative and positive values, this is suggesting that we're getting input of new melt, so we're creating new rocks, but we're also recycling them. So that's quite active in a tectonic space. And then this period here, so 2.1 or 2 billion years down to 1900, this is actually a really weird age for Northern Australia. So we get them only occurring in the Pine Creek origin, in the Central Block and in the Halls Creek. And we can see this really dominant zigzag pattern where we're obviously sourcing rocks which are radiogenic, but at about 1850, we're really only sourcing something that is more evolved, more reworked. But then by about 1720, we've changed and we're pushing towards more radiogenic, and we've got that very large spread again. So suggesting we're very much in an active tectonic area. So what I want you to take away from this mostly is that when we're in the McArthur Basin, the western domains, so the Tomkinson Province, the Birrindudu Basin, and the Beetaloo share much more affinity to each other, with a provenance boundary between that and the eastern Beetaloo Basin and other parts such as the South Nicolson Basin. The Palaeo Proterozoic zircons are largely restricted to the Halls Creek and Pine Creek, and the possible source for those really radiogenic zircons I was talking about could also come from those areas as well. That's the only other known juvenile igneous rocks within the Northern Australia. And the other option is that they, one, been eroded away, or they come from outside of Australia. So another possible option is North China. So we're putting this into a lithostratigraphic framework. This is work done by Johan Suarez, and we're looking at a seismic line here, which is this seismic line coming through here. And so This is the Wilton package, the lower part of the Wilton package. And we can see as we go across this daily water fault, it thickens dramatically. And we also have the upper Wilton group on top of this. Now, in the west, we don't really have any of the Wilton package. So what this is showing me, is that we have this changing thickness across the basin. Now, that would suggest that this provenance boundary we're seeing is also something we're seeing within the seismics as well. And so this is really supporting our interpretation of the detrital geochronology. So now I'm going to take you into a chemostratigraphy whirlwind. And we're going to focus on the glide package for this, because my talk would go for a billion years if I did what I did for the rest. Now, sedimentary rocks are an amazing archive for carbonates, an amazing archive for telling us something about our paleo environment, our redox, and what those sediments were experiencing, as long as they haven't been altered after. So you can do a lot with organic rich shales and dolomites and carbonates. So all you've probably heard me say today is clastics, carbonates, shales, sands. So in our basin, that's really all we have. So the proxies we can use are carbon isotopes, and we can also use radiogenic strontium isotopes. So with carbon isotopes, generally it's quite a complicated cycle, but you're looking at the dissolved inorganic carbon within the oceans. And generally this cycle is actually, affected by a lot of processes, but one of the things that it is affected by dramatically is life, is biological activity. So if things are photosynthesizing, they're taking in the light carbon, that's making our pool heavier. If things aren't doing very well, our ocean is going to have much more of that lighter carbon. Our strontium in the oceans is relatively well mixed. The signal, which is much like mantle is, however, we get these fluctuations when we're getting massive inputs from the continents. And all I'm going to talk to you about in the organic rich shales are redox trace elements today. There are many, many more things you can do with these beautiful rocks, but that will be it for now. Okay, so the McArthur Basin, the Barney Creek Formation, 1640, this is where our mineralization occurs. And within the McArthur River mine, they have about 237 million tonnes of zinc at about 9%. And so this is quite a large resource. So understanding the paleo environment is not only important just for us, but it's also quite important for them. So the hole I'm going to be looking at right now is this one here called LV009 and sits within the McArthur Basin in what's called the Batten Fault Zone. So this is a carbon isotope curve. As I said before, if things are doing really well, you will get more of a positive excursion. So things will go towards the right. And if you're getting life not doing very well, things will go towards the left. Now, it's much more complicated than that, but we're just going to take that for now. And what you can see in the Barney Creek Formation is what I want you to draw your eyes to, is we see this -2 per mil trend, and it's progressively getting heavier, and we're getting this shift in the isotopes as we go back up into the carbonates. Now, if we have a look at the strontium curve, so this is radiogenic strontium, we can see that we get these really prominent fluctuations in strontium within the Barney Creek Formation. So this is what seawater looks like. So we can see it's really shifting from seawater. Now, that sort of suggests that we're probably looking at something that's not a marine signal, that we're looking at something that's much more restricted likely, because we're sourcing more material from the continents. So this is what it would kind of look like. So if you have carbonates here in your open marine, and then when we're getting these higher strontium values, we're getting organics being deposited in this lagoonal setting, and we're getting much more radiogenic strontium. So that's all well and good, but can we use any of this to compare it across the basin? So people do chemostratigraphy, use it as a correlation tool. And so I've plotted up a series of different columns. So this is the one we were just looking at, LV009. This here is the Birrindudu Basin. This is Mambaloo. So this is kind of the main geographic spread, but I've also plotted in some work that Dana is doing in her PhD in the Tina deposit, in the Batten Fault Zone, and also some stuff Marcus Kunzman did in Lamont Pass 3. I've coloured things based on their formation, so you can easily see it. But what we do see is this nice -2 per mil, roughly. It changes a bit in the Barney Creek, and we see that in all of our sections. We also see it shifting towards much more positive, shifting towards heavier values as we're going into the reward dollarstone. So yes, we can use carbon isotopes to see across the basin and to use these as a correlation tool. So it suggests that these were in the same paleo environment when they were deposited. So if we then have a look at some redox elements within the glide package, I've got molybdenum and vanadium. This is amazing work done by Darwin. And what we can see is that I've plotted them only the two most geographically spread. So one in the Birrindudu Basin, now that's represented by circles, and the one in the McArthur Basin is shown by squares. So why we look at things like molybdenum, so moly is quite good in that in oxic environment, it remains stable. It's quite unreactive. When we go into more anoxic environments, it starts to precipitate into the sediments, the organics act as a sink, and we start taking it from the water column. And so what we can see in here is we get these really nice linear trends. So both in the vanadium and in the molybdenum. And so what we see, I'm only going to point to the moly just for ease, but from 0 to 1%, there's no real linear relationship. So that's generally because they're unreactive, so there's no relationship with total organic carbon. So this is organics within the shale. As we go between 2% or 1% and 4%, what we do see is we start to see these linear lines happening. And that's because the moly and the vanadium are being taken or being precipitated or accumulating in the organic material. And when we get to above this in euthynic conditions, so where we have more sulfidic, the sulfides become a competitive sink with the vanadium and the molybdenum. And what we see is this relationship breaks down. And so if we have a look at the relationship between these two elements, we can also sort of start to unravel some more. So vanadium generally will come out of the water column, or it more readily accumulates under suboxic to anoxic conditions, whereas molybdenum doesn't. And so when we get these higher vanadium molybdenum ratios, we're in a more anoxic environment. When we start to see this sort of downward trend, this is suggesting that we're in a more euthynic environment. So we've got more sulfides. Now, what we can see from all of this is that the Frains Formation, which is over here in the Birrindudu Basin, remains under euthynic conditions for a longer time. Now, if you were an explorer, that would be a great thing for you because it would be promoting mineralization or SEDEX deposits. So one thing about basin systems is they're really hard to date. So without your tuffs, your volcanics, you're kind of screwed sometimes. So there's been a lot of work being done at the University of Adelaide, particularly by Darwin. And what I'm going to talk to you about now is looking at uranium and dating carbonates with them. And so what Darwin's actually been doing, this is a case study again from the glide package. We're up in a place here, Balverini and Abner Range, and right near a beautiful place called the Heartbreak Hotel. These age rocks are about 1612. This is where his sample comes from. And what he's been doing is he's essentially imaging and rastering across these carbonates using a laser. So he'll collect 1 millimeter scale regions for geochemistry and for geochronology. So We can collect uranium, lead isotopes, but we can also collect those things that make us worry. So diagenetic indicators, aluminium. So that makes this technique really approachable for people. And what we find is we get really nice data out of it. So this is manganese strontium. This is a diagenetic indicator for carbonates. And then the colors represent uranium concentration. And so what he actually does is you can actually have thresholds where I only want to look at low aluminium zones. And I want you to show me where the manganese strontium areas are, and you can avoid those areas. So you're essentially picking your domains to date. And what you get is this beautiful Concordia plot and an age which fits within uncertainty of the tuff ages. Now, the uncertainty is a little higher than a tuff, but in a Mesoproterozoic system, plus or minus 19, seems pretty good to me. Now I'm going to take you on a little side tour because Darwin's also just started doing the same thing, but for rubidium and strontium. So we could do the same thing for shales. This is not from the McArthur Basin. This was only done a couple of weeks ago. It just was very cool, so I thought I'd show it. This is actually from my honours student work, Matt Barnett, and he's working in the Loch Lillies Cars Belt, much closer to you guys. And we had a go at dating some of his carbonates within a drill hole. Forgive the colour scheme, it's horrific, but it shows what we need to see. So when we map these, we can see we've got these two phases. We've got this veining, this carbonate veining through here. We have these feldspars, and we have these pore filling micas. And so we have two datable phases within this sample. So remembering that carbonate or calcite really doesn't have any rubidium in it, it only has strontium. And when we just have a look at these feldspars, we get this age of 483 plus or minus 12. Now, this data hasn't been really cleaned up or anything, but it's a really, really good age. So work that GA has done in that same sort of area shows that this is with uncertainty. And we also get this other age of 363 plus or minus 39 when we look at the micas. And this fits within the tabarabarin as well. So we're actually pulling out really interesting data by this new technique that Darwin's been doing. Now, that was a complete sidestep. I just wanted to spruik how awesome Darwin is. But what I want to bring you back to is our McArthur Basin. So chronostratigraphically, the detrital record shows changes in provenance. Using multiple data sets, that's what I'm trying to emphasize. It's not just about detrital, seismics, chemostrat, it's about all of them together. We can pick out spreads in provenance. We can use chemostrat to go across basin-wide, but what I want to emphasize is that we do actually get a lot of local variation. So when comparing these to a global record, you have to be quite careful because basins are not homogeneous systems. So not everything is a global record. And also putting this into a lithostratigraphic framework, we can use seismics to help us pinpoint where we're getting our depicenters and our basin bounding faults. So I want to just finish off with this quote, which was from a paper in the McArthur Basin. So a prolonged period of stability in crustal dynamics, redox state and surface environments and planetary climate. Now, yes, compared to the Neoproterozoic, the Mesoproterozoic is pretty stable, but we see the configuration of Nuna and we see it going towards Rodinia by 1 GA. We get fluctuations in our basin redox. We get these in stream environments, get Eusinia, you get amazing base metal deposits, and you're getting these massive petroleum source rocks. And we're getting evolving tectonics showing us we're getting altering pathways of sediments. So it's not really boring billion, it's just, you know, it's a kind of cool billion. Thank you.
Thank you very much, Morgan. I like that kind of cool billion. It's got a catch to it. Yeah. Anyone got any nice questions for Morgan? Yeah.
You said you were mentioning about salinity or something. Was that of McArthur Basin.
I'm sorry, could you repeat that about paleo
Yeah, so I
salinity?
think at the very beginning in the intro, you mentioned you might have looked at salinity as well in the basin.
Yeah, so we're also trying to use stable strontium as well in conjunction with radiogenic carbon to have a look at, and sedimentology to try and find ranges in salinity. But we haven't, I don't have any of that here to show you, but I probably could give you a bit of a rundown later if you like.
Yeah.
Yeah. Nice.
Awesome. George?
Geoscience Australia went to a lot of trouble when they went through the Isa region.
Yep.
Subdividing the region up into 3
Mhm.
super basins, if you like.
Yep.
And that terminology is fairly well established in literature.
Mhm.
You've taken Rowdy's or Rawlings, I guess, terminology. But if I look at what you've put up from Rawlings versus what GA has, there's quite a difference in terms of the major boundaries. So if you were to use sequence stratigraphy to
Mhm.
do your correlations, I think you can find that you can take those 3 super basins from Isa across into certainly the southern McArthur and probably northern McArthur, and also further to the west. So can I ask, why did you adopt the Rawlings nomenclature as opposed to the GA stuff?
Mainly because we're working in the Northern Territory, that is the nomenclature that they primarily use. But what we're trying to adapt to do, and when we try and publish papers, we're actually trying to put it in both frameworks. Because at the moment, there are those 2, which you're right, they should just be one. But at the moment, it's not that simple. So we're trying to use both. I speak from a Northern Territory point of view, just because that's where I've worked most. And I haven't really worked a lot in Isa, so I've not adapted that. But we're always bearing in mind the same sort of, if that makes sense. It's just at the moment easier, but we're trying to use both.
Yeah, because I can take sequence stratigraphy from an Isa.
Oh,
And I
100%.
can apply it to Tina,
Yeah.
out the river.
And I think that's sort of the point, at the beginning I was making. It is actually a really vast system, and it can be correlated right across. The issue being is that when you have state surveys, they don't often talk. And so we have had both terminologies being within the literature. It's just now about doing it in a way where we try and kind of put forward both alternatives until they do start doing seamless geology across. And it is only just a habit that I use NT geology.
Yeah, I guess the point I was trying to make it, if you look at what's happening in the exploration industry.
Yeah.
They're looking for a target.
Mm.
So they want to zero in a particular part of the stratigraphy.
Yeah.
If you use the sequence stratigraphy approach, then it's really cut and
Yeah.
dry then.
Yeah.
Then you look at the top of the individual super basins,
Mhm.
and you can do the same. I know you do it in McArthur.
Yeah.
I know you can do it further to the west.
Yeah.
So I'm just worried that it's going to confuse industry if you use 2 different sets of methods.
Yeah.
I know you're trying to marry the 2,
Mm.
but maybe by prolonging one,
Yes. Yeah.
it just adds to the confusion.
Yeah, 100%. And I don't disagree at all. It is something that we should look to change as we're moving forward, and when we publish the final kind of overview. Welcome.
We don't want to make it too easy. Jochen.
Yeah, you had this great image, Barney Creek formation, strontium isotopes and carbon isotopes.
Yeah.
Maybe you can jump back to that.
Yep.
But 3 questions.
Mhm.
Firstly, you probably said it, but I missed it. What was there any interpretation, any explanation for the negative isotopic excursion? How do you interpret that?
So basically, where I think essentially the basin's going into anoxia quite quickly and eusinia, and it's essentially everything's just acute. So we're getting restriction and accumulation of those organics as our basin is just becoming more stratified and more anoxic.
Okay, and I also understand that the basin became much deeper during that time, right? The Barney Creek formation
Mhm.
was the deepest point of the entire basin.
Yep.
How can you explain that the entire basin became more restricted at the same time the entire thing was actually subsiding? You would expect sort of the entire basin becomes more open rather than more restricted when it's all sinking. And then one information is a lot of clay in it.
Yep.
How do you know that the strontium isotopes are not affected by increased clay input?
They would be infected. They'd be
By
infected.
clay, I mean, all the formations up and down, above, and below,
Yep.
Barnacle formation.
All
is
carbonates.
Pure carbon,
Yep.
so it's easy to develop strong.
Yeah, 100%.
But the Barnacle formation is really rich in clay.
Yeah.
So it's more difficult to do.
Yes, no, of course, but I suppose you have to be getting that radiogenic signature from somewhere, right? And so to be getting increases in radiogenic strontium, that has to be coming continentward, right? To be bringing in those excess in more strontium. So without that, you still just, strontium so well mixed in the oceans, it's not going to change that much. So
Well,
even in a deep
well,
shale.
Yeah, sorry, you're right there, of course, but
Yeah.
what I mean is, the strontium might simply not be dissolved strontium, but it's right.
Ah, sorry. Yes, of course. Yeah, possibly. We do, I mean, you do get quite a lot of fluctuation. So whether you're just getting more not dissolved strontium in those more radiogenic samples, potentially 100%. I don't really have an answer for that, other than that's the interpretation we've gone with. So I do agree, we do get it, but you do get quite deep. I mean, you can look at some areas like Baikal, something like that. It's incredibly deep lakes, right? So just because it is a deep water facies doesn't necessarily mean you can't have a restricted body. And I mean, I suppose when you think about the McArthur Basin, is it really ever completely open? Because we have these continents all around us. So it is kind of its own big basinal environment.
Another question.
Nice.
Yeah, sure. Yeah.
I think very interesting that the northern Chinese craton is so similar.
Yeah.
The colors is similar.
Yeah.
The biomarks are also similar. Everything is similar. It's quite stunning. Do the Chinese do any similar studies, so zircon provenance studies, to see how these two fit together?
No, so no, they haven't yet. I tried to, but unfortunately the literature is so flooded, it's actually quite difficult to do. So I have had a look at trying to compare detritus to it. And what you do see is more likely they're receiving our detrital signature rather than we're receiving theirs, because I was trying to look for the source of those incredibly radiogenic zircons. So, but I would honestly need to spend a lot more time trying to sift through literature. But no, they haven't done detrital work doing provenance. But yeah, it is something that I have started to attempt to do and then admittedly gave up. But yeah. Yeah.
And my question. So I guess you presented a whole load of different techniques and so on with different implications, some for water depth, paleo environment, biological activity and so on. What are the consequences of all this if I'm an exploration company? What tools have I gained? How would I use these kind of things?
Oh, 100%. So particularly, so for both petroleum and exploration, when you look at a petroleum sense, right, they're looking for your source and they're looking, and so to have a source, you need to have a lot of organic matter, and you need to have the right sort of temperature rocks, right? So what we're doing is we'll go through and we'll look at stratigraphy and go, yes, we've got a lot of organic matter here. These are formed in anoxic environments. These will be perfect to have a look for oil and gas in. The same thing actually applies to base metals. So petroleum industry and exploration companies don't really realize they use the same techniques. In a lot of those environments, you're either looking for redox traps, so you're looking for something for the fluids to precipitate out in. So you're giving them an idea of what the chemistry of those rocks are, even if it is secondary mineralization coming through. The other thing is understanding where you are in stratigraphy is, I mean, in a pile of sediments that kind of all look the same, it's so important. And so trying to help to narrow this down, I'm not saying that we're doing any better than anyone else, but we're providing at least more of a framework for people to work with. And so companies find that invaluable. Also, at the same time, you know, we do a lot of analytical work and that's very favorable for them because they just get the report that we give them, right? So petroleum and minerals companies find it incredibly useful using all these techniques because it's something they don't have to get their head around, that we do, and we sort of give them what we think is happening. But especially these novel dating techniques, we found that and using seismic. So there's a lot of seismic which has been shot in the Northern Territory that industry and more mineral companies don't really use because that's not the techniques that they've sort of been brought up in, I suppose. And so we have a PhD student who's looking at joining all the seismics together and doing a reinterpretation I know Cyro's done a bit of this as well, but essentially they're finding that invaluable because you can trace these basin markers across and they can use that. So it's kind of, by doing so much, it is helpful for them because they just don't have the capacity, the time, or the inclination to be doing these sort of studies.
Okay, awesome. Any more questions? All right, well, thank you very much. Thanks to Morgan again. We'll be heading out for dinner and a drink somewhere after this. So if anyone's interested in joining that, just come up to me afterwards and we'll arrange a plan. Okay.